So for part A, we just wanted to find the area of region S. They give us the function for region S, and they tell us the bounds on it from 0 to root pi. All right. So all we have to do for this one is know how to use our calculator and remember the formula for the area of a region in polar coordinates, which is 1/2 the integral of r squared d theta. So we have 1/2 of the integral from 0 to root pi of our function 3 root theta sine theta squared d theta. And when you plug that in your calculator, number one, make sure you're in radians. Number two, you don't need to bother to convert to polar coordinates or anything. Just type these in as x's and get an answer. And hopefully you got 3.534. Does that sound good to everybody? All right. Perfect. So 2 points for that, 1 point for having the correct integral, and 1 point for getting the correct answer at the end. And then part B says, what's the average distance from the origin to a point on the curve from 0 to root pi? Well, the distance from the origin to a point on the curve is just r, right? That's what r is defined as, right? Theta tells us how far we go around, and r tells us how far out do we go. So the distance from the origin to a point on the curve is just r. To find the average distance, that's just the average value of a continuous function. So this ought to just be the mean value theorem for integrals, 1 over root pi minus 0 times the integral from 0 to root pi of the function 3 root theta sine theta squared d theta. No need to square it. And we have our constant out in front. And with any luck, that came out to be 1.580. And you have 1 point for having the correct integral and 1 point for getting the correct answer on that one. Everybody good with A and B there? All right, part C. So part C says we want to draw a line through the origin that has a positive slope that takes S and divides it into 2 regions that have equal area. So we'll pretend that I've done that. We want to write, but we don't need to solve an equation involving 1 or more integrals that gives us the value of m. And so we already know the total area, right, of the entire region to be 3.534. So one side of our equal sign should just probably be equals 1/2 of 3.534. But the other half of it, we're going to have to sort of figure out. We're going to have to figure out how to write an integral that represents the area from here to here. So just this section. And so it's still going to be an integral of our function squared with a 1/2 out in front. And we're going to integrate from 0 to something, but we got to figure out what that theta value is right there. And so how do we figure out what that theta value is? Anybody find a good way to do that? We're looking for the slope of this. So how do we represent the slope of this line? Let's just talk in x and y coordinates. How do we represent the slope of that line? Should be a change in y over a change in x, right? And that would just be to find the coordinates of this point. Right, if we're looking for the coordinates of this point, that could just be written as x comma y. And so we could then say that the tangent of theta is equal to y over x, right? Isn't that one of our equations in polar coordinates? And the slope of this line should just be equal to, since we're going from the origin to y over x, should be equal to our slope. And so what's the theta value that we are at when we are at the point x comma y? If tangent theta equals m, then that theta value ought to be the inverse tangent of m. So if we just put inverse tangent of m up here as our upper limit, and we were to integrate that, that would give us an integral expression that includes an m in it, that we could eventually solve for m, because everything else in here is just going to be a numeric value. And we'll solve for m and get an answer. We don't need to solve it, but that's what we want. And that one was, let's see here, 1 point for getting that limit, 1 point for having the area equated here somehow, and 1 point for the entire equation. Any questions on that one? Does that one go okay? All right, and then the last one says, for k greater than 0, a of k is the area of the portion of region S that is also inside the circle k cosine theta. Find the limit as k approaches infinity of a sub k. All right, so what does k cosine theta look like? K cosine theta is just a circle, right, that lies in the first and the fourth quadrants. And as the value of k gets larger and larger, the circle gets larger and larger, staying though still in quadrants 1 and 4. So what happens if k goes towards infinity? How much space, let's say in quadrant 1, is that circle taking up as k goes towards infinity? Well, it should be effectively taking up all of the space in quadrants 1 and 4. It should be expanding out so big that you can't even tell that there's a curve here at the edge, that it's just getting so large. So effectively, as k goes towards infinity, the circle takes up all of the area in quadrant 1. And so the portion that is inside the circle and inside this is just the portion of this that's in the first quadrant. And so this should just be 1/2 of our integral from 0 to pi over 2, because that'd be the first quadrant, of our function r of theta squared d theta, which comes out to be 3.324. And that one's worth 2 points, 1 for having the right limits and 1 for getting the right answer with the correct integral written next to it. Any questions on that?